Harmonics. When do we use harmonics?
Is it a transition?
Resolution?
Call it?
When you turn on the Samsung, you press the button, you select abdomen, abdomen, right? And we start scanning. Are the harmonics working already?
Yeah.
Yes.
Yes, the Samsungs are preset to work on harmonics as you turn them on. Okay, so what are harmonics? When you think of harmonics, what do you think?
Harmony?
Synchronized.
Yeah, synchronized. For me, when I saw harmonics, I thought of both thumbs in harmony. It's because I'm old. Okay, so harmonics has different frequencies that are put together in unison to make music, right? Okay, like an orchestra, they all have different instruments, but they harmonize. Okay, when things are in harmony, what does that mean?
They sound bad.
That they sound better, right? They sound better. Things are working, right? Like right now, my life is in a harmony. That's been that way for a very long time. It's in a harmony. It's amazing. One day you guys will be there too. Okay, so we have linear and non-linear behavior. When you think of linear, what do you think of?
Straight line.
Okay, so if I drew a line from point A to point B, we could retrace how I got there, right? Just follow the line. It's predictable. Okay? And we have nonlinear behavior. What do you think of nonlinear?
Unpredictable?
It's unpredictable. Okay? Who can give me some examples of linear behavior?
My grade.
Is directly related to your performance? Okay, so we can say the clock, right? This clock in the back, it has a hand that moves every 60 seconds, right? And we have another hand that moves every 60 minutes. And then we have a hand that moves every second, right? Okay, that's linear behavior. We can tell the time by looking at that clock. What's nonlinear behavior? Something that's unpredictable. Huh? No, a plane should be linear.
Yeah, you went.
Point A to point B.
Sabrina, you're really stuck on that plane.
The weather, right?
Oh, yeah, okay.
Okay, the weather. Yep. There's a forecast where it says that it's gonna be sunny all day, but then all of a sudden it freezes. Okay, it's unpredictable, right? So which one do you think ultrasound uses?
Linear.
Linear, okay? A typical ultrasound machine will use linear behavior because it's predictable. And what does the machine do?
Calculates.
It calculates. And the best way to calculate something is to know what you're calculating, right? Okay, so the ultrasound machine has a fundamental frequency that is linear. Okay, so when I say fundamental frequency, we're talking about the frequency that the machine is set at. Okay, each machine is set at different frequencies. Okay, so what is harmonic imaging? Harmonic imaging is the creation of an image from sound reflections at twice the frequency of transmitted sound. Okay, so I want you guys to imagine the propagation of sound through tissue. Okay? Is it just a straight shot from the probe to the liver?
No.
No? What is it encountering as it's propagating?
The skin.
Skin, okay, but break it down even more. Subcutaneous, exactly. And so the subcutaneous has different cells than the fat, right?
Yeah.
And the fat has different cells than the muscle. The muscle has different cells than the connective tissue, right? Okay, so let's imagine that we're walking through a hallway that's filled with balloons, top to bottom, filled with balloons. Can we get through that relatively easy?
Yes.
Yes, right? So if we're in a straight line walking through a hallway full of balloons with an equal space between each other, will that space get deviated at all? No, right?
No, yes,
No, right? Right, we could still walk with that arm's length in between each student without any deviation, right? Okay, but what if I put some water in some of those balloons. What's gonna happen to the space between us?
It's gonna get closer.
Compressed.
It's gonna get closer once you hit those balloons, right?
Mhm.
And then what's gonna happen afterwards to the space?
It gets wider.
That's gonna expand, right? Okay, so, do we know where those water balloons are at?
No.
No. Okay, so at that point, our behavior is non-linear. It's not predictable now, because now we have an unpredictable distance between us at a point in which we don't know where that, where that space is gonna deviate, whether it's gonna get smaller or larger. Okay, so do you think that happens in the body at any point?
Oh, yeah.
Yes, okay, naturally that happens. Because sound is going through all these different cells with these different propagation speeds, these different tissues, with different propagation speeds, with different attenuation rates, okay? So it creates non-linear behavior, okay? So let's say that a machine has a fundamental frequency of 2 megahertz, what will the harmonic frequency be? 4, because the harmonic frequency is twice the fundamental frequency. Okay, but how does that happen? Okay, so which do you think is better, 2 megahertz or 4 megahertz?
4.
Depends what you're standing, but 2 megahertz.
No, so we're not talking about PRF, we're just talking about the
Oh.
frequency.
It would be
4.
4?
4, right? Okay, so if we look at this image right here, we have this diameter of the fundamental frequency, and then we have the diameter of the harmonic frequency. Do you guys remember?
Interference?
Huh?
Like it interferes with each other?
No,
It's the smaller areas of the
exactly, okay? The equation for intensity, you guys
Oh.
remember?
Power of 4.
Huh?
Raised to the power of 4?
No.
2?
No. 2. No, it's not power. What is it? Intensity is equal to
power area.
power over area squared, right? Because there's 2 different, okay? So according to that equation, which one has more intensity?
4.
The harmonic.
The,
Smaller area.
because it's a smaller area. Smaller area, more intensity, right? Okay. So more intensity is good because our images look clearer, right? Right?
Yes.
Yes? Okay, so, let me try to explain how that works. What are you laughing at, Nicole?
It's hard. I think this is the hardest one so far.
You got that right? He's laughing at me? Okay. So what this is telling us is that we have a fundamental frequency that is linear, right? Let's pretend that all of these are equally spaced with an equal amplitude, right? Okay. But as sound is propagating through tissues, there's a difference in spaces, the cells in the tissues deform, so it, so all of that stuff influences the shape of these waves, or the propagation of the waves. So within these fundamental waves, there is nonlinear waves, okay? There's nonlinear waves. Through constructive interference, these harmonics get more intense, okay? The nonlinear waves get together and they become more intense. Okay, so the harmonics that we use start at twice the fundamental frequency, but they can get much greater than that, okay? There's up to, I think, 8 times the fundamental frequency, okay? But for imaging, we use twice the fundamental frequency, okay? So Okay, so let's just say that our machine is 1 megahertz. How many of these waves are being sent out? Of the fundamental frequency, how many waves are being sent out?
4.
Our frequency is 1 megahertz.
Oh,
1.
1.
1 million per second, right? 1 megahertz
Oh, okay.
equals 1 million per, oops. Per second, right? So just imagine 1 million of these fundamental frequency waves, okay? Those are predictable, those are easier to see, right? Okay, but do you think there's as many harmonics as there is fundamental?
There's double.
No.
Oh.
No, okay, so how random do you think it is for them to constructively interfere? Like, what are the chances of them constructively interfering to create an image? What do you think?
50-50.
50-50, okay, so let's just say at the most, there's 500,000 non-linear waves, okay? So which is easier to calculate, 1 million or 500,000? 500,000, right? 5,000 options, okay, 500,000 options?
Yeah.
Okay, so this is why fundamentals, this is why harmonics also works at making a better image because it's easier to calculate. Okay, so what happens is that the machine cancels out the fundamental frequency. Okay, it tells the processor or the crystal, I don't wanna hear any frequencies of 1 megahertz. All I wanna hear is 2 megahertz frequencies. So it cancels out the fundamental frequencies and all we're left with is this more intense sound wave that makes a better image.
Okay. So what I'm kind of getting is getting rid of kind of the low echoes or the low.
It's not the low echoes, it's a fundamental echoes. It's a fundamental echo. Okay, because the machine is set at say 1 megahertz, right? Okay, so the machine knows to cancel that one out.
Mhm.
And what are we left with? With the harmonics.
And is the harmonics the constructive interference?
Constructive interference, yes. Harmonics are obtained by constructive interference. Okay, so on the Samsung machine, there's a harmonic button and there's an S harmonic button. Have you guys seen the difference between those? No.
No.
Okay, we'll go to the lab. Okay, so let's just go through this next slide really quick and then we'll go to the lab, okay? All right, so the fundamental image. Fundamental, what are we talking about?
Basic.
Basic, okay, which means the machine preset, right? What the machine is supposed to be imaging it. Okay, so the fundamental image, the image created by processing the reflections that have the same frequency as a transmitted sound. Okay, so if we have a 5 megahertz ultrasound machine, it's gonna be focused on the frequencies that are 5 megahertz. Okay, does that make sense to everybody?
Yes.
Yes? All right, now for harmonic imaging, the image is created processing reflections that are twice the fundamental frequency. So if our ultrasound machine is at 5 megahertz, what's the frequency of the
10.
harmonics?
10.
It's 10, okay, just twice. Okay, so a significant percentage of studies are suboptimal because sound beam attenuation. What does it mean to attenuate?
Decrease in intensity.
What?
Decrease in intensity as it travels.
Yes, a decrease of intensity, okay? So as sound propagates, does sound get
Attenuated.
bigger or smaller?
Small.
It's smaller, right? Okay, so it attenuates. Harmonic imaging is useful in improving images because harmonics undergoes less attenuation. Why do you guys think?
It's a higher frequency.
Because
It's
it
longer.
has to penetrate deeper for it to work.
Okay, so where does the fundamental frequency start? Or where does the sound start from in the fundamental frequency?
Lower
At the transducer. Where do the harmonics start?
body.
In the body, as they're traveling through the body. Okay, so there's that space already that the harmonics already doesn't have to worry about. Okay, so it technically it travels less distance. Less distance equals less attenuation. Okay, we're gonna go ahead and stop there. You guys, you guys are bumming me out. You guys look so sad.